Alright guys, so our last two videos were all about parallel lines, and today we'll be discussing perpendicular lines. You do need to print out the notes for today, so make sure that you have those in front of you, okay? You'll also need your compass and your straight edge, so get those out as well. Alright, so before we get into the really nitty-gritty stuff, I want to show you a couple pictures. The first of these is from the San Francisco Cable Car Museum, and it's all the tools they use to actually build the cable car system, okay? So I know we have a straight edge here. Now I know it looks a little bent, but there's glass protecting this, so the picture kind of warped the shape of the straight edge. But notice, they didn't use a ruler. They used a straight edge, and look at the size of this compass, okay? Imagine this dust brush fits in your hand, okay? Imagine the size of this compass. Huge, right? So imagine you're building cable cars and their routes with an actual compass and a straight edge, okay? That wasn't all that long ago. Alright, and then here's a picture of actually the cables. What happens is the cables get fed into this and run across the streets all times. And the cable car just grabs the cable and it pulls it along. It releases the cable when it wants to stop. So these right here would be wonderful and great examples of parallel lines. And the reason they have to be parallel is, well, you know, if they're not, then they would intersect at some point, and do I really want my cables to all be getting mixed in together? The answer to that is no. Okay, I wouldn't want to be on that cable car when that happened, okay? So just remember that sometimes I share fun, interesting facts about my life. So this is my trip to San Francisco, and it could be asked of you tomorrow on a pop quiz, okay? So just keep that in mind. I might ask you where I went. I might ask you what museum I visited, which is the Cable Car Museum. Okay, so just keep that in mind. Alright, so before we get too much farther, we have some vocabulary that we need to discuss. First off, perpendicular lines, as a refresher, just means that the two lines meet at a 90-degree angle. Okay? And we use that little square, that box, to indicate that it is a right angle. Alright, now a perpendicular bisector not only meets, and the two lines don't only meet at a 90-degree angle, but one of them cuts a segment into two equal pieces. It cuts it in half. Remember that we learned what bisector meant when we talked about our constructions. Alright, so the question is let's construct a perpendicular bisector, okay? This is actually done exactly the same way as finding the midpoint of this segment AB. So you're going to put your point on A and open it to more than halfway. Okay, make your mark, and then without changing your compass, do the same thing from point B. Alright, so now I have my two arcs, and I can put my compass away, and then where the two arcs intersect is going to be the perpendicular bisector. So let me get that real straight there. Oops. It's not entirely perfect. I am drawing after all. Alright, so that is the line. That is a perpendicular line that runs through line segment AB and also bisects it. Okay, so it's no different than creating the bisector before. The bisector that we create will be 90 degrees. So reflection question, how can you use your ruler and protractor to check your methods? Now we can use a ruler to measure and make sure these are of equal length. We can also use a protractor to verify that that's 90 degrees. So I'm actually going to pull out my protractor. Let's see where this is, right there. Alright. And then I'm going to make sure I put the vertex of the angle right here in the center. If you have a little hole, that's where it goes. And the one ray of the line needs to be at 0, and then I measure and I get it, so that's spot on 90 degrees. Okay? So we can use a protractor and a ruler to measure the lengths and the angle to verify that it is in fact a bisector and a perpendicular one. Alright, so make sure that you have that reflection jotted down on your notes. Now, a couple more things that we need to know. First off, the shortest distance from any point to any line is a perpendicular line. Now, so if I have a point, and then I'm going to draw a line. Here we go. Alright, here's this line. the shortest distance to travel from this point to this line is going to be a perpendicular line. Okay, so I'm going to show you what I mean. Okay, I can travel out here, that's a long way to get there, or I could just travel straight down. That, in fact, this perpendicular line right here is the shortest distance I can have. Okay, and the distance from a point to a line is going to be the length of this segment that you see here. From here to here, this length right here. Okay? So using perpendicular lines to find the distance from a point to a line. So we have here that we're starting at point P. What distance is the shortest to line AC? Is it AB, or excuse me, AP, BP, or CP? The only one of those that meets at a right angle is B. So I'm going to say line PB is the shortest distance. Now we need to write and solve an inequality for x. We know that PA has to be greater than PB because PB is the shortest length. So we'll say x plus 3 is greater than 5. And all we did was substituted PA for x plus 3 and PB with 5. Now we can move the 3 around, subtract 3 from both sides. That's the addition property of equality. And so we have that x is greater than 2. And that is your inequality for this problem. Alright, what I'd like for you to do is take a minute and try this problem, and then we will come back and confer. Alright, so it says name the shortest segment from point A to line BC. Well, the only line that goes from point A to line BC and is perpendicular is line AB. And then it says write and solve an inequality for x. Well, we know x minus 5 is the shortest distance, so 12 is greater than x minus 5. So we can add 5 to both sides by the addition property, and I'm going to get that 17 is greater than x. Now another way you can write this is we can also say that x is less than 17. Either one of these is acceptable. Alright, so another terminology here is reflection, okay? Remember that if you look in a mirror, you are seeing your reflection, okay? So let's say in this case that we have a line and we'll name it line L. Line L would be the mirror, and triangle ABC is looking into the mirror and it sees its reflection. You know how when you're looking in the mirror and you raise your left hand, it looks like the person in the mirror, you, are raising your right hand. It's because it's a reflection, okay? Now, another important note here is this blue triangle is labeled ABC. But this red triangle, this red triangle is labeled A prime, B prime, C prime. That means that this was our original, and this was the reflection. Okay? So that's important to know. Alright, so given that point P is on the perpendicular bisector of the line segment AB, we need to prove that AB is congruent to BP. We need to prove that AP and BP are of same length. So I'm going to do 2 tick marks, right, because we already have one set here. Alright, so we're going to use the property of reflection. So, since PM is the perpendicular bisector, and I'm going to use a paragraph proof, but feel free to make this a flow proof or a 2-column proof, whatever you want, okay? So since PM is the perpendicular bisector of line AB, line segment AB, then we know that AP and BP are reflections of each other. Okay, so going back to the picture of the triangles, the distance from C to line L and the distance from line C or C prime to line L are the same length. Okay? If you get closer to the mirror, your reflection gets closer. If you back away, your reflection backs away. It is mimicking. So since we know they are equidistant, points A and point B are equidistant from this line, we'll call it line L, and we know that the line is perpendicular to the line segment, okay, they have to be reflections of each other. And since they're reflections of each other, so therefore, since they are reflections, AP has to be congruent to BP by the definition of reflections. Alright, taking a look at this problem, sometimes you'll be asked to create a perpendicular line to point M, to line M. Notice here that I have a line, okay, it has an arrow on one side, it really should have an arrow on the other side, my bad, let me fix that. Alright, it's fixed. So now we cannot bisect a line because we can't cut forever in half. However, we can draw a perpendicular line to it, okay? So remember that the shortest distance from point P to line M is a perpendicular line, so we can draw that. Now, the first thing that I did here was put my point, or my compass on point P, and then I drew this arc here. And notice that it crossed line M in two places, A and B. Now that I have these 2 points, all I have to do is put my point on A, okay, draw an arc that's more than halfway, and then switch and do the same thing from point P, or B, excuse me. Alright, so I move my compass away and draw my line. Alright, so by construction we can say that this line here is perpendicular to line M and it passes through point P. Okay, I can move point P anywhere else and do this again. The process is exactly the same. Okay, and that's all we have for perpendicular lines for today, and I will see you guys later.